lecture of mixed signal IC design. So we are discussing about different architectures of digital to analog converter, and we discussed in detail about resistor string DAC with the non-linearity, the errors which can come in the resistor string DAC. Today we will see one another DAC which is called as R2R ladder DAC. I think you would have definitely heard about this architecture, or you would have heard about the other version of this where we use a binary weighted resistor DAC. So there are two types of ladder DACs. One is called as binary weighted resistor DAC, and this is R2R ladder DAC. So R2R ladder, the DAC which we are going to discuss now is a slightly improved version of the binary weighted DAC. In binary weighted DAC, you will have resistors with binary weight. Say for example, in R2R, if there are only two resistors, R and 2R, that is those two resistors we'll use in R2R ladder DAC. But in the binary weighted resistor DAC, we'll have a series of DACs. We will have a set of resistors, but the values of that resistors are binary weighted, in the sense 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. In that way, the resistor values will be there. Now, the reason why we are not discussing that is because getting binary weighted resistors and especially to provide matching or exactly binary weighting resistors, getting those resistors are a little difficult, and for that reason, due to the mismatches in the resistor values, that will result in non-linearity. So that is why we are going for a better version than the binary weighted DAC. Right. So here I'll be discussing this with a maybe I'll take a 3-bit DAC example, and with that I'll explain. So as the name suggests, in this digital to analog converter, we use two resistors. One resistor of value R, then other will be 2R. And the digital input, what we'll have, so basically the input data is digital, right? So that digital input, based on the digital input, we'll be routing the connections, and the output is taken from the with the help of an op-amp. Basically, there are two versions of this DAC. One is called as current mode DAC, and another one is called as voltage mode DAC. So here, from the R2R ladder structure, we'll have a ladder kind of structure. So from this ladder structure, we'll be getting a current, and that current will be tapping across. We'll be measuring that current across the voltage connected across in the feedback loop of an op-amp, and thereby we'll get the output as voltage, right? So the basic architecture is, basic structure what we have is, as we know, we'll be generating the analog output from a reference voltage. So we'll have a reference voltage, and from the reference voltage we have R and 2R structures. We'll have an R and then we'll have a 2R. So this is R and this is 2R. So depending on the number of bits of the DAC, so say for example, if you have 3-bit DAC, you will have 3 sets of R and 2R. So this is the first set, this is the second set, and this is the third set. There will be 3 sets of R and 2R for a 3-bit DAC. Similarly, for an n-bit DAC, you will have n sets of this R and 2R in the form of this ladder, and this will be terminated with the help of another 2R. This will be terminated with another 2R resistance value. Now we can see that the 2R structure. So the structure is like this. Now we have to provide the digital input data, right? So that digital input data a second. The data will be presented to the bottom end of this 2R resistor. At the same time, so we say for a 3-bit DAC, we know the input data. What we can write is maybe D2, D1, D0. The data will vary from 000 to 111, right? So depending on the input digital data, the data will be connected to the to this resistance. the 2R resistance, the bottom end of the 2R resistance will be connected to switches. Through switches, it will be connected to the digital input data. So when the switch is high, it will be connected to and from here, if the switch is high, what we know is, say for example, D0 is high. When D0 is high, the corresponding resistance will be connected, and that will make sure that a current will flow from the reference voltage Vref through the specific resistor, and that current will be taken across the feedback resistor across a op amp. So the rest of the structure is like this. We'll have an op amp here, minus and plus. The plus terminal is grounded, and in the minus terminal we connect a resistance here. So this resistance, you can call it as RF. Now we'll have two lines here. One is to the virtual ground of the op amp, and another one is actually to the actual ground towards the non-inverting terminal of the op amp. Now the connection goes like this. So we'll have either this is how it is connected. So depending on the input digital data, so the data will be presented at this point. So this is the D2 location, this is D1 location, and this is D0 location, right? So depending on the input digital data, the switch here will be connected either to this node or to the other node, right? So it will be switched either to this node or to the other node. That means the digital input data determines whether each resistor is switched to ground. Ground is connected to the plus of the op amp, or it is connected to the virtual ground, the inverting terminal of the op amp, right? Now, so if it is connected, so when the switch is connected to the inverting terminal of the op amp, what happens? A current will flow, and the current will be flowing across the RF resistance. That is how this works. So let us see in a little more detail. So now you can see that the resistance connected here is 2R, right? Now say if this is connected to ground, if this resistor, this 2R resistor, if this node is connected to ground, the resistance seen here is 2R parallel to 2R, which is equal to R, again which will come in series with R. So R plus R will be 2R. Then again for the next thing, that 2R and 2R will be again parallel, that will be again R, then R plus R 2R. So that is how the resistors are connected. The resistors are in this fashion. So what happens here is, if you look at these nodes, here, each node voltage is actually related to this reference voltage, but that is through a binary weighted relationship. That means through this ladder, if we move from right towards the left of this ladder, we can see that the reference voltage is actually is divided in a particular fashion, and you will get a binary weighted relationship when you are placing R and 2R resistors. Let us see how it is, right? Say for example, can you tell me what will be the voltage at this point? So anyway, one thing you can see, the switches what you have here, the switch will be connected either to actual ground or to the virtual ground, because these 2 points, so this is an op amp in a negative feedback mode, so voltage at non-inverting terminal will be equal to voltage at inverting terminal, so both will be connected to ground. So there is whatever may be the case, the current flowing from the reference voltage source through the resistors will be equal. The only thing is whether I'll get the current, whether that current is flowing to the ground or the current is flowing through the resistance RF. That is only difference, right? So if this is connected to, if this point is connected to this switch, this point, the current will be flowing to ground, but on the other way, if it is connected to the other end, it will be flowing through the resistance RF. That is only difference, right? Yeah. So when you look at the voltage at this point, what you can say is, since when you look at the combination here, it is coming R2R, R2R. So what I have here is basically an R. So can you tell me what is the voltage here? Yes, the voltage here will be Vref divided by 2. Similarly, what will be the voltage at this point? What will be the voltage? Yeah, this will be Vref divided by 4. And the next node voltage will be Vref divided by 8. This is how the node voltages will be, right? So if you look at the node voltages, you can see that there is a binary weighted relationship because of the voltage division in the ladder, and that voltage that is specifically due to the relationship between the resistor values, because we use R and 2R resistance values, right? Now as I mentioned before, the total current which is flowing here, see the current, when I consider a current which flows from this Vref resistance, whether the switch is connected to left side or right side, the current remains constant, because both sides it is connected to the ground or virtual ground. In one case you are actually getting that current through the resistance RF, the other case the current will be flowing to the ground. That is only difference. So the total current flowing from the reference voltage is constant, and since for that reason, see since this is connected either to virtual ground or to ordinary ground, the potential at the bottom of every resistor can be considered as 0, right? This voltage can be considered as 0, because for virtual ground and ordinary ground, the only difference is voltage will be 0. The current can be, in a virtual ground you cannot expect any current flowing to the input terminals of the op amp. Since we have a resistance connected over here, that current can be flowing through current can flow through the feedback resistance RF, right? So therefore the node voltages, so these voltages what I have marked here as Vref by 2, Vref by 4 and Vref by 8, these node voltages will remain constant for any value of digital input. These voltages will remain constant, right? Based on these voltages we will be getting a current. Now how can I write the output voltage? So this is the output voltage, right? So how will I write output voltage? Output voltage can be written as this node minus the drop across RF. This node is at 0, so 0 minus drop across RF is the current flowing here. So if I mark this current as say I out, we can write it as I out into RF. This will be the output voltage, right? Now how will you write this I out? That is the only thing which we need to find here. If you look at the circuit, we need to know what is I out. So what will be I out? I out is the sum of the currents selected by the digital input. So I out is a current flowing here, that means the current coming from this point, but this will be the sum. So this can a current which can flow from here, the current coming out from here, or current coming from here, and that will be based on the combination of the inputs what we have, right? So we need to write a relation for I out. How will I write relation for I out? I out or I total? So I can I out, yeah. So the relation for I out can be written as, and this current is dependent, or current will be a fraction, it will be a function of the digital input data, right? So say for example, if I want to know the current flowing through this resistance, the rightmost resistance, which is corresponding to the LSB, let me write that first. We'll current due to LSB switch. What is the current? What will be the current due to this LSB switch? Let me call it as I naught. Is it okay now? Whether my voice is okay? Is there any disturbance? Is it okay now? All right. Okay. Yeah. So what is the current due to LSB switch I0? When I0 closes, this switch closes, what is the current? Can you tell me what is the current? We know the node voltage here. The node voltage is Vref by 8. that quantity divided by the resistance value. The resistance value is 2R. That will be the current flowing here. This, right? So that will be Vref divided by 8 divided by 2R. So I can write into 1 by 2R. That will be the current due to LSB switch. Similarly, the current due, so this is corresponding to D0. Now the corresponding to the D1 switch, if I write this I1, what I can write is Vref divided by 4 into 1 by 2R. This is how I can write the one second. Yeah, so this is how I can write that. Similarly, if I write for the MSB switch, which is I2, it will be Vref divided by 2 into 1 by 2R. So what I have written now is, if only D0 is closed, I will be getting current. I will be getting only this current, which is Vref by 8 into 1 by 2R. If the D1, the second switch is closed, you will be getting only the current through that branch, and the MSB switch is closed, we will be getting current only through that branch. Now, when your data varies from, the digital data varies from 000 to 111, it will be a combination of this, right? So D0, the current due to this plus this one, current due to this or this one. So all the combinations will come depending on the input digital data. So if I generalize this expression, I can write it as I output can be written as it depends on the digital input data, right? So I'll just take the digital input data, and that data value can vary. So say for example it is K, it can vary from let me mark K vary from 0 to n minus 1. For an n bit DAC, we put the digital input data from D0 to D2. For a 3 bit DAC, D0 to D2. So for n bit DAC, it is 0 to n minus 1. So this K will vary from 0 to n minus 1, and what we have here is the reference voltage divided by 2 to the power of what should be the factor here? When it is LSB, we are getting 2 to the power of n. When it is the middle switch, it is 2 to the power of 2. So it is 2 cube, it is 2 square, it is 2 to the power of 1, right? So while generalizing, what we can write is, we can write this as 2 to the power of n minus k into 1 by 2R. This is how we can write the output current expression. This is clear? Say for example 3-bit DAC, what we have taken here for a 3-bit DAC, and for the first position, when k equal to 0, the quantity will be Vref by 2 to the power of 3. Alright, is this clear? Can I get some response in the chat about this R2R ladder DAC? Alright, yeah. So this is simple one. This is simple DAC where you have to get the current, and based on that current you can write the output voltage expression. So let us solve, let us write one numerical, and yeah, let us look at this question where we have alright, this is a 3-bit DAC which is using a R2R architecture. Given that the value of R is 1K and RF is 2K and Vref is 5 volt. Yeah, so one thing what we neglected in the discussion is yeah. So we are using switches. We did not consider the resistance of the switch, right? So when we discuss about non-linearity, we need to consider that, or we need to rectify those what is the non-linearity which will come due to the switch resistance. That we'll see little later. So as of now, you can neglect the resistance of the switches. What you have to do is you have to find the value of I total, which is the output current. You can consider this as I out for each digital input, and the corresponding output voltage V out. So how will you solve this? The very first thing is you can draw the circuit diagram. You can bring the circuit diagram. and based on the circuit diagram you can in all the design questions you are supposed to even mark the values as well in the circuit diagram. So I have just pasted the circuit diagram here. Now the reference voltage is given as 5, so that changes we can make here. This is 5, so correspondingly you can write the values at this node. These 3 nodes you can write the values, right? And given that R is 1K, so we can easily write what are these resistors, right? So R is 1K, so this 2R is 2K, and this is 2R, 2K, and the feedback resistance, this is also 2K, right? So what we need to do here is we can write D2, D1, D0, then we need to find the output current I out, then we should currently find the V out. So for every input digital data 000, 001, 010, these are the input digital data, right? Now it is easy if you can find the current through individual branches, like what will be the current flowing through the rightmost resistance branch, and if you know the individual currents, so then with those currents you can actually sum up the currents and find the rest of the things. Alright, so you can solve it, and if you have any questions please do ask. So this will be Vref by 2, so this node will be 2.5 volt, and this is Vref by 4, which is again by 2, which is 1.25, and Vref by 8 will be equal to 0.625 volt. These are the node voltages. Right. So for the first, when your D2, D1, D0 all are 0, we are not there will not be any current, because all these 3 switches will be connected to this ground. There is no current flow through the 2K resistance. Therefore, the output also will be equal to 0. That is what is expected. Now, when the digital input data is 001, the first 2 switches are not connected. It is still connected to ground, but the third switch is connected to the op-amp inverting terminal. And what is the current value there, which is the Vref by 8 value we have. So the current value there will be equal to 0.625 divided by 2K. That will be the current. Now what will be this voltage? This voltage can be written as this current value into 2K minus what we are getting is negative voltage. So I out into 2K minus voltage. So similarly you can find the rest of the things. So if you are getting the values, please do let me know for every input data. So for the next one, if you find for this one, next one, and one more for 100, the rest of the things it will be easy. You can add the current for the corresponding bits, and thereby you can write the final output value. So what is the current for 0.625 by 2K is can I get these values, the output voltage values? Are you guys solving? Let me know the value. So the DAC architecture is very simple. This is the architecture. Depending on the number of bits, you have to construct the ladder first, and based on that the node voltages you can write. From that you get the current, and that current value multiplied by the resistance will give you the output voltage. So I think here 0.625 by 2K will be equal to somewhere around 0.31 milliamps. It is 0.31 milliamps. Based on that you can write V out. So V out here is 0. Yeah, this is minus 0.625 volt. So I think then 0, 1, 0 with double of this, right, into it will be Vref by 4 by 2k. Yes, I out in multiples of 0.3125, right. So I'll just write down the value. This is 0.625. All this is in milliamps. 0.9375, 1.25, 1.5625, 1.875 and 2.1875. These are the values for the corresponding digital input data, and the output voltage is minus 1.25, minus 1.875, minus 2.5, minus 3.125, minus 3.75 and minus 4.375. So here you can see in all the cases, since we did not consider any mismatch in the resistors, you are perfectly seeing the increments, and you can say that your DNL will be equal to 0 and INL will be, there is no DNL INL error basically when your steps, when you have an equal ideal increment. Also we can say that the full scale voltage will be 1 LSB lesser than the reference voltage 5. That is what you can see there, no? 4.375 is the full scale voltage, right? So this is all about, this is not all about 3-bit R2R ladder DAC. We'll continue this R2R ladder DAC. We'll also see the the mismatch errors in this, like what is the solution for that. The rest of the things we will see in next class. So if you have any questions here, then please do let me know.